This is our 5th U.S. Center at the Conference of the Parties, and we are really happy to be here and see some familiar faces in the crowd. We had a great week last week, and we've got a lot more interesting presentations coming up this week. So we hope to see you at many of these presentations, both today and later in the week. My name is Amanda McCarty, and I will be the MC for this event. For those of you who are visiting us for the first time, we'd like you to know that the U.S. Center is a public diplomacy effort sponsored by the U.S. Department of State. It is used to highlight efforts that the United States is engaging in both domestically and internationally aimed at understanding, adapting to, and combating climate change. We feature U.S. government activities, as well as activities of U.S. researchers, businesses, and organizations to provide various perspectives on U.S. efforts. Our presenter today comes from the academic research community in the United States. Dr. Jennifer Francis is a research professor at the Institute of Marine and Coastal Sciences at Rutgers University in New Jersey in the United States. She has a Bachelor's of Science in Meteorology from San Jose State University and a PhD in Atmospheric Science from the University of Washington. In her approximately 25 years of academic work, she's founded and directed the Rutgers Climate and Environmental Change Initiative and has taught courses in satellite remote sensing and climate change issues. Dr. Francis's research focuses on Arctic climate change and its effect on climate change across the globe. She will speak today about some new research she is working on in this area. So with no further ado, I will turn it over to Dr. Francis.
All right, well, thank you very much, Amanda. Thank you, everybody, for coming. And today I'm going to be talking about two of the more conspicuous aspects of climate change. Extreme weather in mid-latitudes being down where billions of people live, and the fact that the melting Arctic is so conspicuous. The sea ice is disappearing, glaciers are disappearing, and even permafrost is disappearing. So whether these are linked to each other or not is a very hot topic of research. It's only been around for the last couple of years. It's what I've been focusing on for the last couple of years. And we'll be talking about some of these very new results and hopefully convincing you that they are, in fact, connected. So just to get started, I wanted to show you some examples of literally some of the very extreme or even wacky weather that we've been experiencing just in the last couple of years. So this is up in my neck of the woods, up in Massachusetts. Last winter, we were battered by nor'easter after nor'easter. Of course, Boulder, Colorado, we all know that they experienced an unprecedented flood event just last September. In Alaska, 2 summers ago, they had unprecedented flooding in southeast Alaska. Central Europe, this is all around the northern hemisphere. Just this past spring, again, unprecedented flooding. And I'm sure people here in Poland know well about that. Even Greenland has not been immune to flooding. You don't usually think of Greenland and flooding in the same sentence, but in summer 2012, this is what it looked like in Greenland. And then there's been the cold. The last several winters in Europe have been very, very cold and snowy, and that snow and cold has extended all the way down into the Black Sea and even the south coast of the Mediterranean. And some of the inhabitants and citizens of Eastern Europe have not been happy about this situation. Northern Japan, a place that gets a lot of snow, has had even more snow than normal. I don't know if you can see that picture, but these are people down here. And that snowbank there, it's really hard to imagine the snowplow that they used to clear that road. And then, of course, there have been the heat waves. Typical picture of a heat wave, but what makes this picture special is that it was in March in Burlington, Vermont, where the temperatures got up into the 80s in 2012 of March. And of course, we know that there's been heat waves and droughts all across the United States in the last few summers. Marinas in Texas are no longer marinas, and Eurasia has experienced its own plague of droughts and heat waves. So what do these events that I've just described have in common? They're all related to weather patterns getting stuck. And this is the kind of extreme event that I'm talking about. I'm not talking about hurricanes. Well, actually, I'm going to talk about Sandy later a little bit. But what I'm talking about in terms of extreme events are those that are related to weather patterns getting stuck in one place. So the question becomes, what the heck is going on here? We're seeing these kinds of events increasing, and in particular, what people are starting to ask is whether human-caused climate change is playing a role in these events. This is a prickly question for scientists up until not too long ago. It's really only in the last few years that studies have been coming out attributing some of these extreme events to climate change. And so more and more of us now are willing to step up and say, yes, there is a connection between climate change and these increasing extreme weather events. So let's step back for a second, and I'm sure you've all seen a plot like this many times, but I like to remind everybody just what a pickle we've gotten ourselves into. So here we are looking back in time to the left, about 450,000 years. The red curve there is what the global temperature has been doing over this time period. And of course, we know that it fluctuates due to natural causes, mostly changes in the Earth's orbit, changes in the sun, things like that. And following very closely with that temperature curve are changes in carbon dioxide. But the temperature change comes first. Carbon dioxide change comes later. But what we see as that we get over towards the recent times is carbon dioxide has shot up very, very quickly. And of course, we all know why that is. All of our burning of fossil fuels. We know that the amount of carbon dioxide in the atmosphere today is the highest it's been in at least 800,000 years. But what we notice is that the temperature has not yet caught up with this very high level of carbon dioxide that we have in the atmosphere now. And we know that's because it takes a long time for that heat that it traps down by the surface to warm the oceans. The oceans require a lot of energy to warm up, so there's a lag in the system. But you should notice, and I'm sure you all know this, but the carbon dioxide now is leading. What's going on? Uh-oh. It's my computer, I think. Yeah. Ooh, that light's not on. Sorry, everybody. Gonna have to start things up again here.
Everybody better start thinking of questions right now so that we have plenty at the end. You have plenty of time right now, so.
You can think about what that picture is. You'll have a quiz later. Okay, hopefully that's not going to happen again. Okay, so where were we? We were in this pickle. So what we know is that the last time carbon dioxide levels were as high as this, as I said, a long, long time ago, the globe was several degrees warmer than it is right now, and sea levels were tens of feet higher. So clearly we've gotten ourselves into this situation that is going to cause a lot more misery for people. But the Earth is starting to catch up to these high levels of carbon dioxide. Here we're going back only 1,000 years now, and I'm sure you've all seen a graph like this as well, and how up until very recently, which again is on the right, temperatures of the Earth were actually starting to go down somewhat, coming actually heading towards the next ice age. But what we see now happening is the temperatures of the Earth are increasing rapidly. 11 of the 12 warmest years on record occurred just since 1998. And we also know that those temperature changes are not occurring uniformly around the globe. And in fact, the Arctic is where the warming is occurring the fastest. And we'll be talking a lot more about that. So not only is the Earth's temperature going up, but it's also the atmosphere is gaining a lot more moisture. As the ocean warms, there's more evaporation, and going back to the 1970s, we see that the amount of water vapor in the atmosphere has increased by about 7% or so. And this water vapor, extra water vapor in the atmosphere, does a couple of things. We know that the water vapor is itself a greenhouse gas, so it's adding to the greenhouse effect. But of course, it's also providing more precipitation. Although that precipitation is also not spread uniformly around the globe. These are model projections for the end of the century with winter or northern hemisphere winter on the left and northern hemisphere summer on the right. And you don't need to see the detail, but the brown colors there are showing you where precipitation is actually projected to decrease in the future, whereas the blue areas are where it's going to increase. And so the sort of basic story is that the dry areas of the Earth are going to get drier, the wet areas are going to get wetter. We see this is already starting to happen with heavy downpours, especially in the United States, and especially in the northeast of the United States, are already on the rise. So between the increasing temperature of the atmosphere and the increasing water vapor in the atmosphere, we've added a lot of energy to the system. And so I like to use the analogy of a deck of cards, where Mother Nature is playing poker. And it's like we've thrown a few more aces and a few more kings into the deck, so that if you were going to play poker with this deck of cards, your chances of getting a really good hand have increased a lot. It doesn't mean you will definitely get a good hand, but the chances are much higher now. So let's focus in now more on the Arctic. And as you probably all know, the sea ice on the Arctic Ocean is not in a good place. Here, let's look back 30 years. This is 1980 in September. When we look down on the top of the North Pole, all that pink stuff is ice floating on the Arctic Ocean. That's what we call sea ice. And this is what it looked like about 30 years ago at the end of summer, when sea ice is at its minimum extent. Well, in 2012, not this past summer, but the summer before, as you can see, things look very different. In fact, the amount of sea ice in the Arctic in 2012 was half as much as it was only 30 years ago. And if you take into account the thickness of that ice and multiply it by the area, you get the volume. The volume of the sea ice has decreased by 75% only in 30 years. And what's left is very thin. It's very vulnerable to any changes in the winds or the currents. So it's been described as rotten and slushy by the people who go up there and observe the ice. But how unusual is this loss of ice? You know, maybe this was just a fluke. Well, we can actually get a pretty good idea of how much sea ice there was in the Arctic going back almost 1,500 years. And this is done by looking at the sediments at the bottom of the Arctic Ocean, and we know that different sorts of plankton live in the water depending on whether there's ice on top or not. So this is a reconstruction, as I said, going back about 1,500 years. You can see that it fluctuates around and about a little bit, but it stays pretty steady until you get over to the far right, where that blue curve is the present day record. And you can see it's dropping right off into uncharted territory. But this plot doesn't have 2012 on it yet. But if we put 2012 on there, it doesn't even fit on the graph. It's a very different place now. So just to drive that point home, if you're not already depressed enough, we've got a really nice animation here that was created by people at NOAA and also at the National Snow and Ice Data Center. And as we start this, I'll explain what you're looking at. So here we are up at the top of the world. And what we're seeing is, okay, you can see the land area. There's Alaska, Greenland, Russia. So the blue and white stuff in the middle of the ocean there is, of course, the sea ice. But the colors correspond to the age of the sea ice that you're looking at. Generally, the older ice is, the thicker it is. And so the white ones, you can see the scale down here on the right, the white stuff is 7, 8, 9 years old, whereas the blue stuff is ice that's much younger, 1, 2, 3 years old. So think thickness when you watch this. So as I put it in motion, what you're going to see is that through the year, the ice grows in the winter and then shrinks back in the summer, and you're going to see the ice revolving generally around the Arctic Ocean in a clockwise direction, and that's because that's the average direction of the winds. This was derived from satellite information, where they would identify a feature in the ice and then track it over time and keep track of how old it was. So let's put it in motion, and what you're going to see is starting in 1987, here are the years down here. And as we go through time, you can see, as I mentioned, the ice tends to move in a clockwise direction. Eventually, that thickest ice rotates out and down the east coast of Greenland into the North Atlantic Ocean, where it eventually melts. And as we get up into the 2000s now, you're starting to see that white ice starting to decrease in the amount of area that it covers. It's almost like an animal watching this, like it's alive. So you can see now we're getting very close to present day, and there's very little of that thick, shoot, I tried to catch it. Anyway, you could see that there was very little of that thick old ice left. Okay, well the year 2012 was not just for the sea ice, but it was a bad year, a really tough year for the Arctic in general. We can look at a couple other things that were going on up there. This plot shows you how much snow there was in the early summer on high latitude land areas, so Siberia, North America, and these bars are showing you how much snow there was relative to normal, starting back in the 60s up to present time. So what you can see is that starting around the mid-90s or so, that snow cover, this was for June, is just disappearing. It's true in July and it's true in May. In fact, the snow is disappearing even faster than the sea ice is disappearing. Now, Greenland also had a very tough year. We can look back and put this into perspective. Starting in 1992, this orange color on Greenland is showing what areas on the top of the snow underwent some melt during the summer. So 1992, much larger area. Only 10 years later, in 2002. A few years later, 2005, a lot larger area. But look at 2012. 97% of the surface of Greenland underwent some melt. And this is the first time it's happened in at least 150 years. And the time before that was much, much longer in the past. We know the glaciers are also disappearing, not just in the Arctic, but all around the world. And this graphic gives you an indication of when you see these red and yellow circles on here, it's showing that the glaciers in that particular area are decreasing in their thickness. And you can see that it's happening just about everywhere. So we're losing the glaciers. In fact, here's an example of a glacier in Austria. This picture was taken about 130 years ago or so, 140 years. That's what it looked like then. And this is what it looked like back in 2003. And there are examples like this all around the world. And of course, this is important because it contributes to sea level rise, just like the melt on Greenland contributes to sea level rise, while melting sea ice generally does not. So why should you all care? Why should, everybody care about what's happening in the Arctic? Well, as I just mentioned, there's the issue of sea level rise. We know that this is already starting to occur. We can look back a couple thousand years actually and see how today's sea level rise compares to what happened in the past. So we've got 2,000, 1,000 years ago, about 100 years ago, starting to get to this area here close to present day. So in the last 100 years or so, we've had about a foot of sea level rise in general around the world on average. But what does the future hold? As you all know, it depends greatly on what we do in terms of our emissions of greenhouse gases. But other reasons are that as the Arctic melts and fresh water enters the Arctic Ocean, it actually affects the global ocean current system. And the changes in the Arctic are affecting the marine food web in the Arctic, which are also having an impact on marine organisms farther south as well. We all know about the increased shipping and the access and the issues related to the retreating sea ice up north, the better access to resources, the oil and the gas. And then there's this issue of extreme weather events, and that's what I'm going to focus in on now. So let's get back to that sea ice, for example, again. So again, we're looking down on the North Pole. This white area is showing you how much sea ice there was in 2012, in the summer of 2012, compared to what it should be, which is the pink line there. And the reason this is important is because you know that ice and snow are very white. They reflect most of the solar energy that hits them right back to outer space, and so that energy never enters the climate system. It never contributes to warming anything on Earth. But as we lose this ice and we have much more open water up in the Arctic now, all that energy instead goes right into the ocean, and it does enter the climate system. It contributes to the warming, and this is part of the reason why the Arctic is warming so fast. So as we add heat to the Arctic Ocean all summer long, by the end of the summer then, most of that heat then gets re-released to the atmosphere. This is what it looks like in the fall in the Arctic. As that cold air moves in over that relatively warm water, all that heat then goes back into the atmosphere in the form of water vapor, evaporation, and long wave or infrared radiation. And in fact, just in 2012, if you estimate how much heat was absorbed by the Arctic Ocean where the ice was lost, it's about the same amount of energy that the United States uses in 25 years. It's a lot. All right, so we've got this rapidly warming Arctic. Here's another depiction of that, showing the warming happening much more up at the high latitudes. In fact, the Arctic is warming 2 to 3 times faster than the rest of the northern hemisphere is. We can see this also with temperature time series, or how temperature is changing in time in different parts of the world. And this blue curve here is for the Arctic. You can see it's rising very quickly, whereas the northern hemisphere, or the northern hemisphere mid-latitudes, is this green line. So you can see that those two are diverging rapidly, especially in the last decade and a half or so. And this is something that we call Arctic amplification, the fact the Arctic is warming so fast. And we know that when the Arctic was as warm as it is now, it was about 125,000 years ago. And again, at that time, sea levels were 6 to 8 meters higher. So why does that matter? Well, if we think about a layer of air from Warsaw up to the Arctic, we know that warm air takes up more room than cold air does. So this layer of air is going to be thicker here in Warsaw than it is up in the Arctic. So if you have some air sitting on top of this layer, then it's like it's looking, and you look towards the north, it's like there's a hill there. And in fact, that air wants to flow down that hill. And that's what's creating the wind that when it encounters the spin of the Earth, we have this wind flowing towards the north, and because the Earth is spinning, it turns it to the right. And this is what creates what we call the jet stream. It's this ribbon of fast-moving air high over our heads that goes right around the northern hemisphere. But what's happening, because the Arctic is warming so much faster, this layer is getting thicker faster in the Arctic than it is here in Warsaw. So that hill is actually getting less steep. So there's less force creating that wind. So in fact, the jet stream winds are getting weaker because of the more rapid warming in the Arctic. And we'll take a look at that. So here we have an actual plot of the upper level winds around the northern hemisphere and what they've been doing since the late 1970s. So this plot here is showing you that the winds are actually, in the real world, they're decreasing over time. And I've also plotted on there what the sea ice has been doing at the same time. And what you see is that as the sea ice has decreased, so has the wind. So this is something that we can observe in the real world. And the decreases in the fall is about 10% on average around the northern hemisphere. And we know that when the jet stream or the upper level winds get weaker, and any meteorologist can tell you this, is that the jet stream tends to take a wavier path as it travels around the northern hemisphere. So it tends to go in bigger waves in the north-south direction. So weaker westerly wind is wavier. That's how you can remember that. But why do we care about these waves? Well, it's because these waves are weather makers. And here is a schematic of what a jet stream looks like as it goes around the northern hemisphere. It's this orange ribbon here, as I described. And the jet stream generally separates the warm air to the south from the cold air to the north. But even more important is that these waves are where we can find the weather that we experience down here on the surface. So if you're under this part of the wave, in this region where the winds are from the southwest over your head, that is where you'll find storms. If you're in this part of the wave, where the winds are coming from the northwest, this is where you find high pressure at the surface. So you've got your storms, your low pressure, and your high pressure. And it's all created by these waves in the jet stream. So we really do care about these waves. Now the other aspect of this is that we know that the larger these waves become, and remember I told you it gets wavier as the upper level winds get weaker, the bigger those waves get, the slower they move from west to east. So here's an example, there's a schematic showing you how when the waves are relatively small, those waves tend to travel quite rapidly from west to east. And so would the weather associated with them. So when the jet stream looks like that, you would experience frequent weather changes in your location. But the bottom schematic there shows you when the waves get larger, then they tend to move much more slowly. And so you tend to have the weather conditions that you have at this time seem to go on and on forever. Remember, think back to the beginning when I showed you those types of extreme weather events associated with stuck weather patterns. These are the conditions that lead to those kinds of weather patterns lingering a long time. So now I'm going to show you another neat animation that was made by the group at NASA that creates the animations that you see over on the hyperwall over there, the Science Visualization Studio at NASA. So these are actual wind data, and what you can see is the colors are associated with the stronger winds, and that would be your jet stream. So you can see that it's not this nice continuous ribbon of air going around the northern hemisphere, but in fact it's quite broken. There are lots of funny swirls and things. It's really quite a messy place. But what I want to show you is that as we rotate down over North America, there are times when the waves are quite small, and I'm going to show this again so you can see it more clearly. And then there are times when the waves increase in their north-south direction, and you can see that they move much more slowly. See, that gets stuck, and then it finally moves. When the waves get big like that, they tend to stay in one place for a long time, and sometimes they even form those swirls, which we call a block. So let's run through it one more time so you can see this. It's such a neat looking thing anyway. I could watch it over and over again. But you can see there's the small waves, and then the waves move quickly across North America, and then the waves get large and they tend to get stuck. That would be a high pressure in this area. And then sometimes you get these what we call blocking patterns, which is when an eddy cuts off in the upper levels. And when you get one of those blocking patterns, the reason it's called a blocking pattern is that it tends to block the weather patterns so they don't move at all for sometimes weeks at a time. Okay, so that's the theory, that's the concept that we're working on. And the question is whether it's really happening or not. Well, I showed you that the winds really are decreasing in the upper levels of the atmosphere, but let's look at some analysis that we've been doing in the last couple of years, just some very simple plots illustrating some of these changes. So one of the ideas is that, in fact, if these waves are getting larger, and we expect the northern extents of these waves to extend north even more because it's getting warmer up in the northern part than it is down in the southern part, that we should see the peaks of these waves, which we call ridges, moving northward. And that's exactly what this plot is showing you. It's showing the northernmost latitude of the peaks of these waves over time. So starting in 1979, this is latitude, and what we see, remember when I pointed out the winds decreasing right about the mid-1990s, coincident with that, we see that these ridges are actually moving northward just as we'd expect them to. And we can also look at the size of the waves and see how those are changing over time. We'd expect them to increase. And in fact, that's exactly what we see. So this is the size of the waves, the distance between the tops of the ridges and the bottoms of the troughs, and we can see that they're increasing as well. So we can also look at how they're changing over time in different locations around the northern hemisphere. And just very simply, this is a plot showing the trend in that northward movement of the peaks of the ridges. So anything above 0 here means that the ridges are moving northward over time. And what you notice is that everywhere in the northern hemisphere, so this is longitude, this lines up with the map above it, you can see that everywhere around the northern hemisphere, the number is positive. So this is telling us that just about everywhere, these ridges are moving northward, just as we'd expect them to. We can also look at, again, the size of the waves and how they're changing with time in different locations around the northern hemisphere. And once again, we see that the values are all above 0, just about everywhere, meaning that these waves are getting larger over time, as we'd expect. What about this idea of the flow becoming wavier? We see that the size of the waves seems to be increasing. And this plot looks complicated, but you can just focus on the colors. The pink colors are saying that in that area, the flow is doing more north-south motion than east to west. And where it's blue, it's actually blowing harder from west to east. But what we see is there's this big swath of area where this is the real world now, so that's why it's so messy. This big area of pink is telling us that the flow really is getting wavier. And if we compare that to what's happening with the slope of that hill that I described that's driving the winds, where this edge is here is showing where the Arctic is warming the fastest. So where you see this happening is where that hill is becoming less steep the most. And so what we see is that this swath is actually lining up very well with the changes in that slope of the hill that I described earlier. And finally, this is some brand new work that I just have been working on the last couple of weeks. And it's looking at the tendency for the atmosphere to do those swirls, those blocking patterns, which are so key to driving these stagnant weather patterns. And what we see is this is over the whole northern hemisphere. Again, starting in the late 1970s or so, we see that there's a definite increase in the frequency of the occurrence of these swirls in the upper atmosphere, these blocks that tend to cause the weather patterns to get stuck. And also plotted on here is the winds that I showed you earlier. So you can see there's a pretty good correspondence between the weakening winds and the increasing tendency of these blocking patterns. All right, so that's the end of the graphs. Now let's look at some real extreme events and see if they fit this story. So here are two examples. Those of you who live in the East Coast of the United States, or anywhere in the East actually, will remember clearly. I already mentioned the very warm March of 2012 that we had, the heat waves in Burlington, Vermont being 85 degrees, for example. We smashed over 3,000 high temperature records during this March of 2012. The very next year, this past March, was just the opposite. We had very much colder than normal conditions in much of the East. So let's see what the jet stream was doing during these two cases that are so different. Well, this is what the jet stream looked like in March of 2012. And it was pretty much looked like this for most of the month. So remember, the jet stream, which is in this blue here, separates the warm air from in the south from the cold air to the north. And of course, what we see is that when the jet stream dips south of you, you're in the cold air, so the west was cold, and we in the east here were south of it in the tropical air. So, but you'll notice also that there was a very wavy jet stream in place. That following year, it looks very similar, but the wave was just in a different place. Again, it was a very wavy jet stream. It got stuck, and we were in the east, we were in the cold part this time. So 2 different years, same kind of pattern in the jet stream, but just shifted. And then here's a couple of particular examples, say the record snows up in Alaska 2 winters ago. What did the jet stream look like then? This is the actual jet stream on one particular day during that heavy snow period. Here's the coast of California, here's Alaska. This gray stuff here is showing you where the jet stream is. You can think back to that animation I showed you of the NASA winds. Well, here is Alaska up in the cold air north of the jet stream, and this jet stream is bringing a lot of moisture up from the Pacific, which is exactly the ingredients you need for a lot of snow. But again, a very wavy pattern. That flooding in Spain that I mentioned 2 Septembers ago. Once again, here's Spain, here's Washington, D.C. Again, a very wavy pattern in the jet stream. So it just got stuck in that place. That's what happens when the jet stream gets into one of these patterns. All right, well, let's mention the Sandy situation, because we had a very similar situation when Sandy came along. Here we have Hurricane Sandy. Look at the jet stream. I'm sounding like a broken record, but that's the situation that was in place. Remember, this was the end of October, and we had this big dip in the jet stream, a lot of very cold air coming down, and then a big bulge, a big ridge in the jet stream with one of these blocking situations, a blocking high over Labrador. So this high was creating very strong east winds up in this part of the world. So as Sandy came up the coast, moving over very warm water for October, the temperatures of the ocean along the east coast were 4 degrees above normal at the time, which allowed the storm to maintain its tropical characteristics. And it was able to move so far north because of that warm water, where it could then interact with the jet stream, and the path of that Sandy took was because it could interact with this blocking high, and those winds pushed it right into New Jersey. So here's what the Arctic was doing at that time. Remember, this was 2012, is the year that we had the record-breaking ice minimum in the sea ice minimum that September. So we're looking down on the Arctic here, and just look at these colors, and they're telling you that the atmosphere is much, much warmer than normal. Here's Greenland here. Here's that blocking high that is associated with the surface high there, bringing all that east wind down to New Jersey, and we had much, much warmer air than normal over the Arctic. So the question is whether, think back to everything I've told you, this extra warming in the Arctic, making that hill less steep, perhaps causing this blocking high to be either stronger or farther north, or maybe just hung around longer than it would have otherwise. We think there is a connection there. We're still working on that. And as I mentioned, as the oceans warm, that allows hurricanes to survive longer, farther north. Remember, this was the end of October, very unusual for a hurricane to come that far north. But as the oceans warm and allows that to happen, and perhaps increases the possibility or the likelihood of a hurricane interacting with a wavy jet stream like this, creating the situation, the kinds of situations that was in place when Sandy came along. Okay, so take-home messages. As I said, many kinds of extreme weather are caused by persistent weather patterns. Think of a drought, for example. If it's dry for a few days, no big deal. If it goes on for weeks, it becomes a real problem. Same for snowfall. If you're in a very snowy pattern for a long time, you get that picture that I showed you from northern Japan. All of those types of patterns, you can find large waves in the jet stream, or even these blocking patterns that I showed you. And these jet stream patterns like that seem to be increasing. And this is consistent with what we'd expect to see based on the more rapid warming of the Arctic. So we think the Arctic amplification, or this extra warming in the Arctic, is playing a role in driving these types of patterns. And so as we continue to add greenhouse gases to the atmosphere, and even with just what we've already got in there, we think that these types of extreme weather events will probably increase. We'll start to see them in all seasons of the year more frequently as the Arctic continues to warm, not just in the fall, but in other seasons as well. So I bummed you all out, no doubt. That's a lot of bad news there, but there is a silver lining to this cloud, I think. And people are able to, I think the conversation is changing, and I think it's because people can see that the Arctic sea ice is disappearing. They can see the surface of Greenland melt in the kinds of plots that I showed you. They can also experience for themselves that extreme weather is increasing. And they're starting to put two and two together. The journalists are noticing this. More and more papers are coming out making these connections. And people are starting to believe that there's a connection between climate change and extreme weather. Even these guys in this anti-science bunker, I think, are starting to get this message. And I think they're starting to run out of ammunition, and pretty soon we won't have to deal with them anymore. I hope. So I'd be happy to take any questions you have. But thanks again for asking me to be here.
Thank you, Dr. Francis. So you had a little time early on, but I imagine that this was quite a provoking talk for questions. So please raise your hand and I'll come to you with a microphone.
Let's not do 3 at a time, though, like they did in the
One
other
at a
sessions.
time, don't worry.
Yeah.
So great presentation.
Thank you.
There seems to be some still conversations about the level of certainty that the patterns that you talked about are linked to increased tropical storm frequency. Is the level of certainty at 50%, or has it gone higher, or is it closer now to 75 or 90%? With how much confidence, when we talk to people, should we make that connection, storm frequency?
Well, you mean tropical storms now you're talking about?
Yes.
Okay.
Because, tropical Sandy, the typhoon, we understand the connection that the science shows between intensity
Right.
and storm severity.
Right.
Now, what about frequency? Has
Okay.
that been established conclusively? Or are we?
No. The frequency of storms is still up in the air. No pun intended, really. Well, sort of. However, the frequency of late season storms, like in October and even November, is increasing. There is evidence that that's happening. And we think that's pretty directly related to the fact that the oceans are so much warmer now. And really, it's all about the oceans in terms of allowing or providing the energy for tropical storms. So we are seeing these late season storms increasing, which increases the likelihood of them interacting with the jet stream. Because when they happen in the summer, the jet stream is so far north that there's much less likelihood that they would encounter the situation that was in place when Sandy came along. But in terms of certainty, I'm not 100%. Somewhere between 50 and 100, I guess, or maybe 70 and 100, something like that. Yes.
So my name is Paul Bergen from Nest in Norway.
Mm-hmm.
This is not really my field, but I thoroughly enjoyed your interesting and most colorful talk.
Thank you.
I'm wondering if you could explain a few things to me. First, one of your initial graphs showed the variation of temperature followed by a CO2
Right.
increase.
Mm-hmm.
Then at the end, we had the strong CO2 increase,
Mm-hmm.
and you said that will lead to temperature increase, but it's the reverse process.
It's the reverse, right.
So you have to explain that to me, how you make that conclusion.
Okay.
And the second thing is, I understand the sea ice in the Arctic was a little bit more extensive this year than
Right.
last year,
Mm-hmm.
and you showed only last year. So how do you explain that?
Okay. So, going back in time, before we had this big increase in carbon dioxide in the atmosphere that we put there, what would happen is that the orbit of the Earth would change, and that would change the way sunshine was distributed around the Earth, which increased or decreased the temperature depending on how that distribution was changing. So let's say it's increasing the temperature. Well, then you start to melt the permafrost up in the high latitude areas, and that permafrost contains a lot of carbon. When it thaws, it releases that carbon either as carbon dioxide or as methane, depending on whether there's oxygen available or not. And so that starts a feedback process going. So back then, temperature changes, thaws the permafrost, releases more carbon dioxide, increases the temperature, melts more permafrost, etc. No, there's papers that have shown that there's about a 700-year lag between the temperature change and the carbon dioxide change, and it's pretty. People are pretty certain that that's what's happening. In fact, the permafrost is already starting to thaw, so we're worried about a big additional positive feedback kicking into the system as we thaw so much permafrost. And yes, you're correct that this past summer, the sea ice did not retreat quite as much as it did in 2012, but it was still the 6th lowest amount of sea ice on record. So it's not like it recovered or anything. It's just there's a lot of noise in the system, and it was just one of those years when the weather patterns were such that it didn't melt quite as much as the year before, but it's still very thin, it's still very vulnerable, and we're still really worried about it.
Thank you. Good morning. I'm Luca Lombroso from Italy, from the University of Modena. I'm a weather forecaster. My question is if you explore or study the role of jet stream slowdown on 2012 cold spell in Europe, and in particular in Emilia-Romagna, my region. We have the so-called nevone, big snow, very, very big amount of snow close to Rimini, Adriatic Sea, more than 2, 3, 4 meters with a lot of damage.
Right.
And also, if you take in account the role of sudden start warming, if it depends of the slowdown, is a cause of the slowdown. Just a comment about 2003, this year slowdown of melting in Italy. The Daniel call it a big boom of sea ice. It's very, very funny, like this. Daniel in Italy call it this year a boom, an explosion of sea ice, but it's, as you say, the 60 low amount.
Right. So I'm sure that if we looked at the jet stream during the time when you had your very heavy snows in Italy, I mean, there's so many cases I could have chosen to show you, and I'm sure the jet stream would look in a very similar pattern to the one that I showed for Spain, for example, but instead that dip would be just west of Italy. So.
Hi, it's Stephen Leahy, journalist with the Interpress News Service. Might be moving into El Nino phase. How does those play into that El Nino, La Nina play into this?
That is an excellent question. I mean, there are many natural variations and cycles in the atmosphere and the ocean, and how, I mean, this Arctic warming is like a new kid on the block. All these other things have been going on forever, and they probably will. So one of the big research issues that we're dealing with is how those other types of variations that are natural are going to interact with this new feature of the Arctic warming so fast. And I'd say we don't know. We really don't know yet, because this rapid warming of the Arctic is only about a decade and a half or maybe 2 decades old. And so we don't have a very long record to work with yet. So we're going to be looking at model output, but you know, the models are not great at simulating El Niños and ENSO cycles, so there's still a lot of uncertainty about how all that's going to play out. I mean, we're kind of lucky that the last couple of years the ENSO's been neutral, so we've been able to see kind of the Arctic effect somewhat on its own.
Hi, My name is Matthew Schertz. I'm with National Geographic in Brazil. And my question is, do you know, are you aware of any similar research for the Southern Hemisphere? And can you tell us anything about the impact of this, what's going on in the Southern Hemisphere? Is it anything like this at all?
No. The Southern Hemisphere, is very different. Antarctica, for one thing, is extremely cold. It's much, much colder than the Arctic. And so if you warm it up a few degrees, doesn't do much because you're still way below the freezing point. And the sea ice around Antarctica melts back to the land every summer and then grows every winter. So you don't have as much of an opportunity for this loss of sea ice to have a sort of a positive impact on the warming like it does in the Arctic, because the Arctic had all this very thick ice that would survive the summer. So when you lost it, then you'd increase the amount of heat that went into the ocean. That's really not happening very much in the Antarctic. What's affecting the Antarctic situation is actually also human caused, but it's the ozone hole. So as the ozone hole has occurred, it's actually caused the upper levels of the atmosphere over Antarctica to get colder, because ozone absorbs solar energy and it actually warms the upper atmosphere when there's ozone there. So because we've lost the ozone during the spring, right when the sun is emerging and the sea ice is at its maximum, then because we don't have ozone there, that atmosphere is getting colder. It's actually doing just the opposite of what's happening in the Arctic. So it's increasing the steepness of the hill. The jet stream's getting stronger, and it's also moving farther south towards Antarctica, away from Australia and the southern continent. So we think that's partly why Australia is having such drought, because the storm track, which is associated with the jet stream, is moving farther south, and not as many storms are affecting Australia.
Can you give me someone I could talk to about that? Is there a reference? Someone you know who's working on that?
I think the best name for you to look up would be Gillett, Gillette. He's in at the University of BC, I think, or University of Victoria in Canada. Gillette, I'm not sure how he pronounces his name. But yeah.
Great. We have a question here in the back.
From the comfort of the couches. Jason Anderson from WWF in Brussels. Thanks for the very interesting presentation.
You're welcome.
The IPCC first Working Group 1 report is just out. I'm just wondering, because of the time delays in assembling that report, is there anything that you've presented today that is perhaps not captured in that, or because it's new, or is it fully reflected in that?
It's really not, because this is really very new. Our first paper came out last March, or March 2012 rather, and that was after the cutoff for research to go into that IPCC report. And because it was so new, I don't think they were comfortable including it, even if it had made the cut. So, a lot has happened since then. There are a lot of groups working on this topic in using modeling and other observations, and so there's a whole bunch of work going on this now. So, I'm sure in the next report it'll be there. But no, it's really not in there.
Right.
Hi, I'm Mike Williams with the Blue Green Alliance, and I actually have a political question. So you made it's an incredibly clear case of the connection or of increasing severity due to climate change. But when we're faced with, explicit, very severe storms, how clear should governments and activists be in saying you're experiencing climate change?
So everybody knows that you can't look at one storm and make a direct link. But what we do know is that in addition to what I was talking about, we know the atmosphere has more energy in it. So any storm that forms now is forming in a different environment. So I think you could say very confidently that, take Haiyan for example, it's in a different environment than it used to be, and that could have contributed to its very unprecedented, or not unprecedented, but very unusual strength. We know that the depth of heat, or the depth of the ocean that was so warm in the Western Pacific, likely contains a contribution from climate change. So there's many aspects. This particular one, the answer that I like to give is that, well, if you're going to lose 75% of the volume of sea ice, if you're going to warm the Arctic 2 to 3 times faster than the mid-latitudes, if you're going to melt all the glaciers, and you're going to thaw the permafrost, then how can there not be an effect on the jet stream, on the large-scale circulation patterns? But what we're working on now is figuring out exactly where, when, what kind of patterns are going to emerge, and if we're going to hopefully be able to pin down a little more, with a little more detail and specificity, the kinds of extreme events that are going to happen in different parts of the world in different seasons. So I think the answer is yes, it's definitely having an effect, but can't really say exactly what it is at this time. I don't know if that's good enough, but it's the best we can do right now, and like I said, there's a lot of work going on right now on this topic. So I think it's really going to become much clearer in the next couple of years even.
All right, it doesn't look like there's any more questions, and we're right up against the end of our time, so it actually works out quite perfectly. Thank you so much for coming and presenting this recent research to us. We look forward to more research coming out of your laboratory and others on this topic, and hope that you all, if you have additional questions, have a chance to discuss them with our speaker afterwards. Let's give her a hand. And there will be more events coming throughout the week, so please grab a flyer, a bulletin, a pamphlet as you exit and come back. We have a lot more excellent talks coming up. Thank you.